I want to show you this, and the reason I'm interested in showing you this, that you should see that most of these are going to end up the same, right? So you have a spring K, our mass x m on a frictionless surface, right? So we need to draw our two bodies. What's our equilibrium state going to be? What are the forces acting on this? Do we have any force acting to the left? What's our delta? For the equilibrium state, what's our delta? So like equilibrium state, right, is we build it and we take our hands off and it might move a little bit. So last time we put the mass on top of the spring, we took our hands off, the mass sank down delta, right? If I build this, take my hands off, do I have any delta? What? Sorry, a couple people talked. The
forces to the left, we have that.
Yeah, but here at our equilibrium, we don't really have any delta. So I'm just trying to get the delta equals 0, right? So there's no equilibrium force that we're going to cancel out like we canceled out last time. Did that make sense? So this one's actually simpler than the last one, is that we have a positive force N acting up, that agreed, and a negative force mg acting down. That one makes sense? And then like Nick said, it's Nick, right? Yeah. So like Nick said, at our displaced state, we're still going to have a normal force N acting up. That makes sense? And then we have a gravity acting down. And we have a force to the left of kx. And why is that force to the left and not to the right? Yeah, because we defined x as right to the positive, right? So if I define x as right to the left, this is going to be kx acting to the right. You'll get the same equation of motion, but all of your signs will be flipped, right? I mean, your signs will be flipped as you work through it, but they'll all cancel out. All right, so do we take our sum of forces? What do we do about our forces in the y? Do we take the sum of forces in the y? Just kind of ignore them, right? They don't exist. Sum of forces in the x, positive to the right. The sum of forces in the x for our equilibrium state equals 0. Boom, easy. Sum of forces x, what is it here? Yeah, minus kx. And why is it a negative?
Against the positive x displacement.
Yeah, because positive x is to the right, and we're acting to the left, right? And then does that equation equal 0? And why not? Yeah, because it's displaced. And we want to store energy in the kinetic state. So now we're going to apply Newton's second law, which is force equals ma, right? Which is equal to mx double dot, which is equal to the positive to the right, the sum of forces in the x, which is equal to negative kx, right? Lots of stuff goes away, and you have mx double dot is equal to negative kx. Which is equal to mx double dot plus kx is equal to 0. That make sense? And is that the exact same one that we got for the last one? But how? One's horizontal, one's vertical. I mean, that's a legitimate question, right? So if we notice that this is the same equation that we got for the last one, right? What does that tell us about the effect of the mass on the equation of motion?
Negligible.
Yeah, it's not. It doesn't change the actual equation, right? So you can have something vertical, you can have something horizontal. Anyone done the one at an angle yet? What? Yeah, right? What do you think they might get? Yeah. So another good one was there's one that's got compound springs, and you end up with something which is mx double dot plus 2kx equals 0. Is that the same thing? The same as this? I mean,
Same structure.
yeah, I mean, they're really exactly the same. It just becomes mx double dot plus k equivalent x is equal to 0. That makes sense? Your equation of motion is exactly the same. The equation is exactly the same. You know, and that really you could just draw as get rid of the equivalent if you want, and boom. Right? Because your system doesn't know that it's got 3 springs in series and parallel. You know, our system only understands that it has 1 spring, and then we can use that to find the natural frequency and to plot how these things solve, right?